did have a few contact me this morning concerned about road conditions. My worst road condition was the parking lot, but on the north side of buildings, things were bad. As I was leaving, my driveway was fine. I saw some other driveways on the north side of houses. It's like, I'm glad that's not my driveway. So, you know, weird. But I think I got everybody their homework back. Any questions on homework I returned from 1.1 and 1.2? I'd asked my grader as he was looking at it if there were anything he identified as problems that I should talk about, and he didn't. But still kind of coordinating with him exactly how the grading. This is out of 10 points. Each homework's out of 10 points. So, and it's not recorded in the grade book yet. I've got it recorded somewhere, but I haven't transferred that to the grade book yet.
You're talking about this homework?
What I returned, yeah.
Yeah, I got it. The answers that are kind of wrong, I think I got it right. That's what the answer key said. You want me to show you later?
Yes, yeah. If it's how it was graded,
Yeah.
that would be something to look at later. If it's how it was done, we could look at now. And also keep in mind, as you look at it, the answers open up while you're working on it, but after I hand it back, then the key opens up. At some point, you can go and look and see more detail to the solution as well with that. And I did ask him to look at how you were doing the problem, not just the final answer, which was a little different way of thinking for him as a grader, to look at the entire work, not just, oh, they got the right answer. But since I gave you the answer, I definitely wanted to make sure that he was checking your work as well. Okay, last time we looked at 1.3, and after we were done, I looked. We didn't make it through all of the lecture, and so I adjusted the assignment. And so definitely as you look in here for the assignment, if there are any adjustments, this was enough adjustment, it didn't fit all in the title, but I think it still shows up for you under there to see. So we were looking at lines, y equals b plus mx, or y equals mx plus b. And as long as we were given the intercept and the slope, we could come up with the equation. Or if we had the equation, we could find the intercept and the slope. But there were some questions here. Are there any kind of questions on these problems? I do plan to collect these today, and then the rest of them will be collected Thursday. Oh. Yeah, I got my date. Well, okay. Yeah, this, what we did today, so the rest, this part is what we collected today. This part will be Thursday. So are there questions on any of these problems? I heard a 7, and then we'll... So 7. Was 7...
It's not due today.
Okay, that's what I was thinking. 7 looked like 1, would be difficult to do, and so yeah, I listed what you couldn't do yet, and then down here had, well, what will be collected. So as I was putting that together, now that I look at it, that may not have been the clearest way to explain what I had in mind on what you were in a position to do today. But yeah, 7 is one of those we've not covered yet. So, did you have one there? 33. Okay. Let's see, 33. So 33, the Federal Reserve held about 16 billion cubic feet of helium in 2010, is being depleted by 2.1 billion feet per year. Give a linear equation for the remaining reserves in terms of the number of years after 2010. So we need to identify, well, what are we starting with and what's the rate of change? So in this case, what we start with here is 16 billion cubic feet. And I think it'll be easier just in all of this to think in billions of cubic feet. I don't want to write all the zeros down. And it's being depleted, so it's going down at they say 2.1 billion cubic feet per year. And they say in terms of T time, the independent variable I'm typically not all that particular about. Whether you call it T or X, it's an independent variable. And so our reserves are, for that matter, I'm not all that concerned necessarily about the dependent variable either. I mean, in this case, the key parts are to realize we do know what we're starting with, we do know the rate of change, and from that we should be able to write down the equation. In any situation, if we know what we start with and how it's changing, we can come up with the equation. The fact here to realize is that we are depleting the reserves, so it's going down. So then B, they ask, okay, what is the reserves in 2015? Well, that's 5 years after we started this process. And so we just plug 5 into this formula we came up with, 16 plus minus 2.1 times 5. That's 10.5. So we actually dropped to 5.5 billion cubic feet. And then C, I think, asks for, if the rate of depletion doesn't change, when would the federal helium reserve be depleted? So the depleted would happen when the reserves equal 0. So when is our equation equal to 0? And we have to solve that equation. We could add 2.1t to both sides. 2.1t equals 16. Divide both sides by the 2.1. Pull out our calculator for that computation. 16 divided by 2.1. So about 7.5 years. So in fact, if this model were accurate, given the time and everything, there's no longer any helium reserves. It would have ended sometime in 2017. Although even when we have an equation like this, it's a little hard to sort of know, for a year, are we talking the start of the year, the end of the year? It's just a model that helps us get a picture, and certainly this would be one, if that were the case, and helium is viewed to be very important, somebody wanted to decide, this is not a good trend. What can we do to change this trend? And with any trend like this that is headed down to 0, we really only have kind of two options. Change the rate at which we're depleting, or somehow add to the amount that we've got. Or find a way to offset the rate it's depleting by inserting more into the system at a, well, preferably probably would one like to at least match the rate it's depleting, if not exceed that rate. But it depends on the situation. Okay. Other questions? 31, is that another one I think that's for the next time? Yeah. Okay. So, since I can see how there might have been some confusion on this, if you didn't get this part to turn in today, I will accept it on Thursday as well with this, and we should get on to 1.4 today as well. So I'll try to be clearer. I mean, I just started saying, what it wasn't, and I said, well, I should say what it was, and then what would be collected the next time. But just as I look at that now, it's not as clear as I thought it was when I first put it together. So if you're ready to turn in that homework now, I'll collect that, or if you want to finish it up a little bit and get it in by 4 this afternoon, that's fine as well. But if there was a misunderstanding on exactly what was due today, Thursday's fine for that as well. So. you look out your window, that would certainly influence your decision. So, okay, well, we need to pick up in 1-3 and try to finish, because not every time we're interested in a line are we told the slope and the intercept. Sometimes we're told the slope and maybe some other point. Other times we're maybe just told 2 points, and neither one of them happens to be the y-intercept. So we need to think a little bit more about, well, how are we going to approach those situations? So if we've got a point that's not the y-intercept and the slope, for the graph at least, we could do like we've done when it was the y-intercept. If we're going through the point 2, 4, with a slope of 3, we know a point is going through, we know the slope, over 1 up 3, over 1 up 3, we could plot some other points. So in fact, I guess I already answered this question. If we move over 1 and up 3, we get another point. We can do that again. And in this particular case, since we're not that far from the y-intercept, I guess we could work our way backwards. If we go back 1, we'd go down 3. And if we go back 1, we'd go down 3. And so we could find the y-intercept. And so our equation, once we have the y-intercept and the slope, so I'll put it in the b plus mx form, y equals b plus mx. But notice initially b was not given to us. Some other value was. Now, the stepping backwards not terribly efficient, especially if this point were a long way from x equals 0 for the y-axis. So for graphing, we just need a couple points. We can do that from a point and the slope. The point doesn't have to be anywhere close to the y-intercept. But for the equation, we do want it in this form. That's the form the graphing calculator would graph for us. So we'd like it in that form. And so, in this same example, if we take our basic formula, y equals b plus mx, we know the slope, we know an xy coordinate, we can plug in what we do know, and the only thing we don't know is the y-intercept b. So if we plug in the 3 values we do have, what do we end up with? Y equals b plus mx. We're going to plug in what we do know in this case. We do know that y is 4, the slope is 3, and the x value is 2. So 4 equals b plus 3 times 2, which I believe is c here. That is what most of you said. So we plug in the x, the y, and the slope that we do have. We now just have an equation and one unknown. 4 equals b plus 6. And my apologies, sometimes in the PowerPoint, the hyphen ends up looking like a negative. It's a hyphen in the organizational structure of the slide, not a negative. We could subtract 6 from both sides and we get b equals -2. So we get the same result we got here. In this case, working backwards may have been easy enough, but if this point's very far from the x or the y-axis, we'd have a challenge working all our way backwards. But this method will always work for us. And we can come up with the equation of the line. Now if we have a table, If we have a table and we look at the average rate of change in y over change in x, change in y over change in x, change in y over change in x, and it's always the same, well, if it's always the same, we do have a line and this rate of change is our slope. So again, we can identify our slope. In this case, it's 3. And we can again use any one of the points to generate the equation of the line. So for this one, let's see, if we use 2, 5, y equals b plus mx, 5 equals b plus 3 times 2, we decided the slope was 3. We used one of the points, we can figure out what the y-intercept is. 5 equals b plus 6, b equals -1. So we can come up with the equation. And notice if we check the other points, when x is 3, yes, y will be 9, or excuse me, 8. When x is 4, -1 plus 12 is 11. All these other points fall on this line as well. I don't think we'll see too many of these, but it is possible we might start with a table where the average rate of change isn't constant, in which case it's not a line. And that's about all we can say at this point. It's not a line. The equation would be a whole lot harder to come up with. If we had a graph. From the graph, we should be able to look and interpret and figure out what the slope is, what the y-intercept is. Although notice we don't have what happens when x is 0, so we either have to kind of extend it backwards or do a calculation like we've done here. But we should be able to figure out the slope. And with the slope at any one of the points, come up with the equation. So let's sort of step through and do that. If we look at this, we should be able to figure out the slope. Let's see, most said here a slope of -1. I would agree with that. Certainly in terms of the options given, hopefully we realize the slope is negative. We are falling as we go from left to right. So 1 doesn't work as a possibility. 8 certainly doesn't work. The can't tell I can kind of see, but I think we can tell here, because certainly it looks like we're going through the point 17. And if we decide some other point, I mean, it is hard to interpret the other point, but I would say 2, 6 probably is a point. Although maybe not exactly 2, 6, and certainly if we come over here, it's not exactly 5, 3, or 5, 4. But if we use those 2 points, the slope is change in y over change in x. The slope is -1. Our slope is -1. What's the y-intercept? So we've got y equals b plus mx. If we use, say, this point, 7 equals b, which we don't yet know, plus the slope times x, 7 equals b minus 1, b equals 8. Which would be c, which I think is what most people said. So again, we can tell, well, we can't tell immediately, but we can do some computation to figure out what the slope, or what the intercept is. But it's not just immediately visible in the graph. Now, let's sort of think of this question. What is the slope of the line? Given that it goes through points 2, 0 and 0, negative 4, or number 2, given the statement that 2x minus y equals 4. And this is one of the data sufficiency questions that appears on the GMAT, Graduate Management Aptitude Test, I believe is what it is, for the GMAT. So, for answering this question, is 1 enough to tell us? Is 2 enough to tell us? Do we need both of them together? Did neither one tell us anything? So what would you say on this one? Is statement 1 enough, but not statement 2? Is statement 2 by itself enough, but not statement 1? No, we need them together. Is either one by themselves enough, or together we still can't figure out the problem? So, here we're not being asked what the slope is. We're just being asked, if we're going to have to find the slope, does number 1 give us enough information to find it? Well, certainly if we're given 2 points, change in y or change in x, we can figure out the slope. So 1 is enough. What about number 2? Well, it's not in slope-intercept form, but it's not that hard to rearrange the equation to get it y equals mx plus b. We can figure out the slope from 2 as well. So actually either one by themselves is sufficient. So the answer here would be D. By themselves, either one will allow us to solve the original question. We don't have to say what the slope is. It's actually 2, but that's immaterial here. The question here is, for finding out the slope, does number 1 give us enough information? Okay, what about number 2? Do we need both of them? Only one, only the other, or we still don't have enough? So that's the idea of a data sufficiency question. So here's another one. What's the equation of the line? 1, given it has a slope of 2. Statement 2, given it goes through 1, 4. This is one where we actually do need both bits of information, which most said. There are lots of lines with slope of 2. We can have a slope of 2 here. There are all kinds of lines with a slope of 2. There are also all kinds of lines that go through the point 1, 4. So there's not just one answer from knowing that the slope is 2. There's not just one answer from knowing the slope, it goes through the point 1, 4. But together, there's only one line that has a slope of 2 that actually goes through the point. We're not asked for that equation, we're just asked, do we have enough information? And when we have both 1 and 2, we do have enough information. We could go ahead and find the equation, be like what we did here, but the question here is not what is the equation, just do we have enough information to figure out the equation? There are also times where one line is not all we want to look at. Maybe we're going to compare two different lines. So suppose we had a salary plan, and I should update these numbers. They don't really make sense in today's economy. But suppose we had one job that starts at $6 an hour, and we're promised a raise of $1 an hour. From that description, we should be able to come up with an equation for that particular job. Yes.
Will there be data sufficiency questions on this test?
On the test, I don't anticipate any. Because, yeah, they are tough, but I want you to at least experience some. And so our equation here is the salary is 6 plus y, 1y. The initial amount plus the average rate of change times the independent variable. So we've got that one setting. So that would be one possibility. We're going to contrast this with a second job. Here we start with $8 an hour, and we're promised a raise of 50 cents every year. So again, we're interested in, well, what's going to be the trend in salary after Y years? And it is the salary equals 8 plus 0.5y. Again, the initial value plus the slope times the number of years is our salary. And if we think about this a little bit, hopefully we realize, well, certainly salary one, or this salary starts higher, $8 as opposed to 6. But hopefully we also realize, wait a minute, we're getting bigger raises in the smaller salary. Eventually it's going to catch up. And at some point, these salaries are going to be the same, and this one, in fact, should exceed this one. So as we think of, well, which job is better, certainly starting out, this job has a higher salary, and that doesn't necessarily mean better. Maybe I should have said which one has a higher salary. This one has one to start out, but long term, this one's going to have a higher salary. And we certainly kind of like to know, well, when does the changeover occur? When are the salaries the same? There'd be a number of factors into which one's better, but we want to look at, with this model, compare the two salaries. Well, with our equations and all of our functions, we could look at them with the rule, information, graphs, and tables. But this is called a system of equations, two equations, both of which we kind of like to solve. Is there some value for the year where the salary matches in both equations? And we could do this with a graph, a table, or the equation. Here, it's easy enough to just set the two salaries equal, essentially eliminate the salary. 6 plus y equals 8 plus 0.5y, and work to solve it. Subtract 0.5y from both sides. Subtract 6 from both sides. 0.5y equals 2. Divide by 0.5 or multiply both sides by 2. And we can see that in 4 years, they have the same salary. 4 years, they're both at $10 an hour. Okay. Now, with that, I think the full assignment for 1-3 is you should be in a position to do. So let's move now to section 1-4, where we're going to talk about exponents. And I didn't update the date here on this. But we're going to look at exponents. My assumption is you've seen exponents before. And probably you've seen all these properties of exponents we're going to talk about. So things like, if we've got a to a power times a to another power, we can add the powers. And in fact, a to a power means a times itself repeatedly however many times. So say a to the third power is a times a 3 times. Mathematicians don't really like to write a lot, so if we can find any way to simplify an expression, we would do that. So we've got n copies of A and m more, well, altogether we've got n plus m of them. Or if we were dividing n copies divided by m copies, well, we've got n minus m copies. And starting off at least, we are thinking positive exponents. In fact, positive integer exponents. That's where the repeated multiplication idea comes into play. Turns out we really want to extend that beyond just positive integer exponents. But starting off, positive integer exponents, if we've got a to a power all raised to another power, we multiply the powers. For example, a to the third all to the fourth. We've got a to the third times itself 4 times. And in each of these, we've got 3 a's. So we've got 3, 3, 3, 3, 4 different times. That's 3 times 4. That's 12 of them altogether. And in general, as we're working with exponential expressions, if we can, we'd like to get just a to a power. That would be the simplest form. Not a product involving a to some power and a to another. If we've got a product raised to a power, we could also consider that as each factor being raised to the power. And if we've got a quotient being raised to a power, another form we could look at that in is the numerator to that power divided by the denominator to that power. And for these two, depending on the situation, sometimes we might want to have the fraction raised to the power. Other times we might want to have the powers in the numerator and denominator. So it depends a bit on the situation, which form we really like to have. But important with all of these is a realization that there are equivalent forms. Sometimes one form is helpful, sometimes another form is helpful. Now, we do need to be very familiar with these, comfortable going back and forth. We also need to recognize there's some things that we might think we'd like to do that really aren't true. Also in these formulas, I think it would be helpful if you realize a to the power just means a times itself repeatedly. Because these two especially, trying to remember, okay, am I supposed to add the powers or multiply the powers? We'll think of what exactly is being raised to the power. How many copies of A do we ultimately have in each of these two cases? Now, we do have to watch if we've got a negative somewhere. Negative a to the n, without any parentheses, does not mean the same thing as negative a to the nth power with parentheses. So we've got to watch. Where is the negative? If it's not inside parentheses, we are just taking a to the nth power. Then we're worrying about changing the sign of that. Similarly with, say, like 2x cubed. If we meant for the 2x to be cubed, the whole 2x to be cubed, we would need parentheses. Without parentheses, we cube the x first, then we worry about multiplying by 2. So we do have to watch when we see expressions, what exactly is being raised to the power. If there are no parentheses, only what's right in front of the exponent, that's all that's being raised to the power. If we meant 2x all raised to the power, we need parentheses. And if that's what we meant, we might even take it a little bit further and say, well, that's 2 cubed, x cubed, or 8x cubed. So it's definitely not the same thing. Another thing we've got to watch is, well, a plus b to the nth power is not just a to the nth plus b to the nth. And this is one that I think definitely kind of throws students for a loop. If we look, well, let's in fact just start with a plus b squared. A plus b squared is a plus b times a plus b. Because that's what's being squared. So it's this whole expression times itself 2 times. From the FOIL technique, this is the product of the first elements, which is a squared, the outside elements, the inside, and the last. And we do get an a squared and a b squared, but there's also a middle term of plus 2ab. In terms of what we looked at in, I think it was section 1-2, a plus b quantity squared is a composition. We add 2 numbers, then we square it. Whereas this, we square 1 number, we multiply, I guess 3 numbers, we square 1 number, and we add up the results. So there's just a different order that we're doing the operations. They're exactly the same, but it's not just a squared plus b squared. Also, if we take a to a power plus a to another power, say 2 to the, well, I think I've got an example next. The best we can do here is factor out the common factor. So if we had, say, 3 to the 4th plus 3 to the 5th, each of these does have a factor of 3 to the 4th in them. If I pull 3 to the 4th out of this, I'm left just with 1. If I pull 4 of the 3's out of this, I'm still left with 1, 3. 1 plus 3 I can do. And so we get a very unexpected looking result here from this problem, because it's really not so much a property of exponent type problem as it is a factoring and then just combining like terms problem. They're not like terms here. When we factor out the 3 to the 4th, we do get 2 numbers that we can actually add. So we do have to watch when we're adding things to powers. These properties deal with multiplication and division of a to some power, or constants times a to some power, when we throw in addition, either before the squaring or in a sense after some powers. Most of those properties aren't really going to apply to us. And as we encounter some more complicated expressions, just as we did kind of in 1-2 a couple times, here was a complicated function. Can we identify what the simple pieces were? Similarly with complicated expressions, there are times we want to get them in another form where maybe there are more pieces, but they're all simpler. And other times, we may have lots of simple pieces and decide, I think if I put all these together and get just one expression, maybe that would be easier, instead of lots of pieces to the expression. So the ability to go back and forth between the 2 forms is an important thing for us. So I do have some examples on some worksheets, but let's look at a few. In fact, let me show one of the worksheets just so you can kind of see what they look like. So here's simplify this expression. Wait a little bit to make sure it settles down, because sometimes in loading it decides, oh, I'm going to change the expression. This is not one where you actually enter the answer in. There's a place you click and it will show you what the final answer is. And then you can say, okay, give me a new problem. So you can work through, come up with what you think the answer is, and then check it. So it's self-checking rather than you put in the answer and it checks your work. You kind of check it yourself. So let's try this one. And again, the dash in the first is not part of the problem. So here, the problem we want to simplify is, what is negative 3x squared all cubed? How does that simplify down? So most have an x to the 6th, but we've got a couple different ideas on what the x would be. But here the 3 is part of what's being cubed. So we've got a product raised to a power, it's each factor raised to that power. Negative 3 cubed is negative 27. X to a power raised to another power, we do multiply the powers. So we do get here negative 27, x to the 6th. And in this case, I definitely think we would agree that's a little easier expression than that. Back in 1-2, when we were doing composition, at that point he said, let's don't worry about simplifying, because that kind of hides how it was composed. Here we're kind of doing the opposite. We see some things that look kind of like composition. We're doing something, then we're doing something else, and we'd really like to break it down into some simpler pieces. When we have constants to a power, definitely squares up to 10 or so we should be able to do, cubes up to maybe 4 or 5 cubed, 2 to the 4th. After a while we'd probably just leave, if it was like 8 to the 7th, we would just leave it as 8 to the 7th. We would try to figure out what that is. We could pull out our calculator, but we could leave it as 8 to the 7th. Let's see, let's try another one. So suppose we had negative 2x over 4y all raised to the 3rd power. Now, as the problems get more complicated, we have to keep these in mind. Try not to do too much in any one step, because it's easy to get lost if you just try to do it all in your head. And if it's all done in your head, it's harder to figure out where the mistake was, if there is a mistake. So we have a fraction to a power, but also we have a little bit of simplification. Negative 2 over 4 will simplify. So depending on what you see to do first, you can either simplify this, or you could expand out the fraction. At some point you are going to have to simplify the constants. It doesn't have to be first. The order in which you do some of these operations is not just one order, but at some point you're probably going to do all the different things that somebody else does. So, if you're comparing your work with somebody else, your work may not look like theirs, but you should come up with the same result if you've both done things accurately. Also, in terms of comparing work, I'm fine with you on homework, kind of working together and comparing work, but keep in mind that won't be something you can do on exams. So if your idea of working together is, what did you get? I'm going to write that down. What did you get? I'm going to write that down. You're probably not going to be prepared for the exam. So copying is not working together. And I think consequences of copying will come by the time you get to the exam and realize, oh, I don't know this material. So doing some working together is fine, just make sure that it really is working together as you do that. So if we simplify this first, we're going to have negative x over 2y cubed. A fraction raised to a power is the numerator to that power over the denominator to that power. The negative is cubed, so it's negative, negative, negative. If you want to put it as -1, that's fine. But we will get negative x cubed. If we raise a negative to an odd power, it's going to stay negative. To an even power, the negative actually goes away. And the denominator, we get 2 cubed y cubed. So we get here negative x cubed over 8y cubed is our final result, which is C here. So again, we've got to watch and make sure what exactly is being cubed, and be sure to cube everything. What if we tried this one? So negative 3yz squared, all cubed. So we've got a product raised to a power, each factor is raised to the power. And y, if we don't see a power on it, that is y to the first power. If you want to write it that way, that's fine. Or it will just be y cubed. So we get negative 27, y cubed, z to a power to another power. We would multiply the powers. So we get here, what is that, b? Negative 27y cubed z to the 6th. And again, depending on the situation, sometimes having it look like a composition might be the form we'd want. For a lot of the things we're going to do in calculus, we'd really rather not have it look like a composition if we can simplify it to not look like a composition. So, let's think of another, say, actually I'm going to skip that one because I'm looking at that, I'm not sure what I meant. Now, these ideas work very well for positive integer exponents. They actually apply even if we get other integer exponents or even if we've got fractional exponents. But we need to kind of think, well, what do we mean by those other exponents? So for example, anything to the 0th power. Well, if we go back to the properties of exponents, what would it mean to multiply a number by itself 0 times? That doesn't really seem to make sense. But from here we might end up with something to the 0th power. If we've got a to a power over a to the same power, using our property of exponents we get a to the 0th. So that's a place that we might come up with a to the 0th. Just a to a power divided by a to the same power. We subtract the powers, we get a to the 0th. But another way of looking at this, well, what's another way of looking at a to the n over a to the n? 1. Now, anything over exactly the same thing simplifies to 1. So a to the 0th power is 1 for any base except a equals 0. We typically, when we're talking the exponential or the powers, we don't raise 0 to a power. 0 times anything is 0. Why would we multiply with 0 times itself repeatedly anyway? It's always going to be 0. But 0 to the 0 we don't try to deal with, because in a sense, a to the 0 relates back to the idea of a division, and we don't divide by 0. What about negative powers? So if we have a to a negative power, what do we mean? So like a to the negative third power. Well, again, we sort of think property of exponents. How might we get an a to the negative third? Well, maybe we have a to the 0 minus 3 power. And here's a case, rather than starting with a more complicated expression going to one simpler, we're kind of going the other way. We've got a to a subtraction. There is a way that can be written as a quotient. And a to the 0 power is 1. So in fact, a to any negative power is 1 over a to the corresponding positive power. In algebra, typically, we don't like negative exponents. So we work to get rid of the negative exponents. In calculus, we actually prefer negative exponents to a division. So there are times if we've got 1 over a to the n, it is far better for us to realize, oh, that's a to the negative nth power, and deal with it with a negative power as opposed to a division. So a to a negative power is 1 over a to the n. We're dividing by a n times. In particular, then a to the negative first is 1 over a. We don't usually write that exponent down. What if a to the negative power happens to be in the denominator already? Well, 1 is a to the 0. So a to a power divided by a to another power. We can subtract the powers. We actually end up with a to a positive power. So if we were to see something like 1 over a to the negative second, that would just be a squared. We certainly don't, either in algebra or in calculus, want both a division and a negative power. In algebra, we typically don't want the negative power at all. In calculus, we don't want the division. We certainly don't want them both. So there's a way to simplify that and get rid of both the division and the negative power. So let's do the first one. What would 4 to the negative third power be then? Anything to a negative power is 1 over that, the corresponding positive power. 4 cubed, we can figure out is 64. So this is a 1 over 64. We don't get a negative of our expression, and it's not just 4 times negative 3. It's 4 times its... With the negative power, we don't even think of it as 4 times itself, negative 3 times. That doesn't really make sense. 4 to a negative power, there's a division involved. What about then 1 over 5 to the negative second power? What are we going to get for this one? A negative power always involves a division, but if there's already a division there, 1 over 5 to the negative second is just 5 to the second. So in this case, 25. So again, we don't get a negative in our expression. It doesn't just say 25 in the denominator. It comes up to the numerator as a positive exponent. In a similar vein, then, if we had a whole fraction to a negative power, since the numerators go to the denominator, and denominators with a negative power come to the numerator, we just invert the fraction and raise it to the corresponding positive power. And so that we can simplify even more complicated expressions. Depending on the situation. In algebra, we definitely don't want any negative exponents left. In calculus, it's really more accurate, I think, to say we really don't, we'd prefer not having division, even if that means leaving some negative exponents in there. I think you're getting these. I think we'll skip a couple of these, but the more comfortable you are, the better. Because we also need to think about, well, what if we have fractional exponents? So I want to make sure I've got time to get through the fractional exponents. What would we mean by, say, a to the 1 over n power? A to the 1 over n power means the same thing as the nth root of a. What we would use to solve the equation x to the nth power equals a. Square roots we can do pretty well in our head, as long as it's exact square roots. Cube roots we can do a few. But in general, if we wanted to know what to the third power equals 10, we would do that with a cube root. Well, another notation for that would be 10 to the 1/3 power. Just different notations. We are probably more comfortable with the radical notation. For calculus, it's actually going to be easier for us to work with the fractional exponent notation. And in fact, for seeing this, if it really is true, well, 10 to the 1/3 power cubed should be 10. Property of exponents. 10 to a power to another power, we multiply the powers. And 1/3 times 3 does give us a power of 1. So we just do have 10 on the left-hand side there. Depending on the situation, we might in fact want a decimal for that. So if you pull out your calculator, say to get a decimal approximation, the calculator actually does, I think, have cube root hidden somewhere under math. Yeah, there's the cube root. Or if we wanted 4th root, 5th root, 6th root, we'd have this. But we could ask, what's the cube root of 10? And it will tell us. Or we can say, what's 10 to the 1/3 power? For the 10 to the 1/3 power, we need to be sure to put the parentheses, because otherwise we'll do 10 to the 1st, and then divide that by 3. So as long as we get 10 to the 1/3, we get exactly the same thing. So again, a situation where there are different forms, and it kind of depends on the situation, which form would we prefer. I don't remember if I mentioned in this class yet, some of my classes we have similar topics about different forms, but certainly if you were looking at going on a mission trip and preparing your testimony, you might have 2 or 3 different forms of the testimony depending on, if you're going to a place where there are a variety of cultures, in inner city, where you might run into somebody from a Chinese background, or somebody from a Indian background, or somebody from a from Russia. I mean, different places. You'd have to have some different forms of your testimony to think of what would best relate in this culture, and in this culture, and in this culture. You don't want different truth in that testimony of sharing the gospel, but you do need to think of which is the appropriate form for the person I'm now encountering. Similarly here, depending on the problem, either of these two forms works fine to come up with a decimal answer. But depending on what else we might do with it, sometimes the fractional exponent form would be preferable, other times the radical form. I think we're probably more comfortable with the radical form. But for much of what we'll do in calculus, we actually would prefer the fractional exponent form. In general, things to a power are much easier to work with in calculus than anything else. And I mentioned on this, we do have to watch if you put in 10 to the 1/3 without the parenthesis, it gives you a totally different answer because it doesn't really do 10 to the 1/3 power. It does 10 to the first, does that power first. Oh, and you want me to divide by 3. So that's actually 10 divided by 3, which is not 10 to the 1/3 power. So we definitely have to watch and be careful. Where are our parentheses? Do we have any parentheses? What is the order of operations here? If n is even, a square root, a fourth root, a sixth root, we probably won't do too much other than square roots, maybe some fourth roots. A's got to be positive. We can't take a square root of a negative. We can't take cube roots of negatives. Depending on your calculator, some calculators struggle trying to take, say, the cube root of -8. But that does exist because -2 cubed does equal -8. I think we'll skip a couple of these too. So what if we've got something other than 1/n as our fractional exponent? So a to the m/n power. Turns out with this, there are actually two equivalent interpretations of this. At some point we're taking a root, at some point we're actually doing a power. It doesn't matter the order in which we do it. We could take the nth root of a first and then the nth power, or we could take the nth power first and then take the nth root of that. Either way is fine. Depending on the problem, one order or the other might be a little easier to work with. For where we're headed in calculus, this is actually the form we prefer. Just leave it in fractional exponent form rather than doing radicals and looking at it. Either way, it's a composition. It is so much easier to look at this just as a to a power. But if we're trying to evaluate this, it may be helpful to realize there are two different ways we could approach this. And again, if we have an even root that we're taking, A's got to be positive. And both of these come from applying our rule of exponents. So, actually I didn't have... Let's look at one example here. So suppose we had, say, 16 to the 3/4 power. Two interpretations both give us the same answer. This is the fourth root of 16 cubed. It should also be the fourth root of 16 cubed. When we can kind of say it to distinguish, the fourth root of 16 cubed, or the fourth root of 16 cubed, with some space in there we can give the two different interpretations. If we didn't have a calculator, which one of those would you want to do? Or which one would you rather do? You may not want to do either one. Which one would you rather do? Did I hear the first one? Yeah. Because we can think, okay, I know the fourth root of 16, that's 2, I can cube 2. I really don't want to cube 16. And when I do, I'm going to get a huge number, and I don't think I'm going to spot, oh, I know what the fourth root of that is. So there are definitely times taking the root first is helpful. There are a few times taking the power first might be helpful. Long term in calculus, what we're really interested in, though, is the realization that if we start with something in radical form, The exponent form is by far the more easy form for us to work with. That's the form we're going to work with, just something to a power. Okay, so that finishes up. We finished 1.3. We've also now done 1.4, and I think we're on track with where the syllabus would have us at this point. And I will see you on Thursday. I think a couple people may have come in late. If so, make sure you get signed in here. In fact, I think these two people came in late. Okay, I noticed there was something about baseball you said that needs to look, so you are. Okay, I'll double check the list, but it certainly helps to know who I'm looking for on there, so. Okay. Thank you.
I missed 3. I think it's just like.
That all
Yeah.
you need at this point. No, this is when it failed. Well, people weren't here to return.
Okay, so we're set. It may be a shit work, but I'll try my best, and I'll just check it on here.
Okay, so I mean, this is in 1.1.
I got 100 on the other one.
Which is close.
And then this is the, I didn't even see that one.
On that 21.
21 system.
That was C.
Oh, I guess I didn't even do B and C, because that's the answer I got for A, I guess I didn't do B and C part of it. Okay, yeah, I missed that one.
So, yeah, but that would.
But then on this one, 27, so
Oh,
I
okay.
did -8 to 5, and I put a bracket to include 5, and then on my next one, I did a bracket to include 7. So the answer is just parentheses with a 6, which means like exclude 6. So wouldn't that just be like a synonym of how to write it? Like just another way to write it, since I'm still excluding 6, and I'm including 5 and 7.
Well, you're thinking just integers.
Yeah, because like the answer is parentheses -infinity to 6 parentheses. So I just did 5 to like include 5 and exclude 6.
Yeah, so what about 5.5?
Okay, okay.
5 and 3/4. So yeah, your answer, you were looking just in terms of, well, if it's an
Yeah, I
integer.
was just- yeah.
That, if it was integers, yes, that excludes 6.
Okay.
But it could be more than integers.
Okay, so just put a 6 and did 6.
Yeah.
Okay, awesome.
So,
And that one I know how to do. I just
much time as I wanted to kind of look through